In today's lesson, we're going to be talking about increasing and decreasing functions. So we want to come up with a definition of what it means to be an increasing function. Well, visually, an increasing function is a function that as I read it from left to right, the function is getting larger. And a decreasing function would be a function that as I read it from left to right, it is getting smaller. So what does that mean algebraically? Well, visually, we can see here, for instance, that from interval b to c, our function is increasing. Algebraically, what that means is, let's say we take a point here, maybe that's x1 on the x-axis, then we take a point here, and maybe that's x2 on the x-axis here. And what does that mean? Well, as I read my graph from left to right, we can see that the function itself is increasing. What that means algebraically is if x1 is less than x2, then f at x1 is going to be less than f at x2. Because keep in mind here, the distance from our point to the x-axis would be illustrated as f at x1, and likewise this would be f at x2. So if x1 is less than x2 is another way of saying that I'm reading the graph from left to right, then its images are getting larger. If that's the case, your function is increasing. Likewise, interval CD and interval AB would be decreasing intervals. And you notice here algebraically how this is working. If I pick any 2 points, and let's say we'll label this x1 as well, label this x2, if x1 is less than x2, so that still ensures that we're reading the graph from left to right, then we have a different outcome. The image of x1 must be greater than the image of x2, i.e. f at x1 must be larger than f at x2, and that'll ensure it's going downwards. So now what we have here is 2 rules to determine algebraically whether a given function is increasing or decreasing on a particular interval. Now this relationship would have to hold for the entire interval. So therefore, for instance, you would say that the function f is increasing on interval BC provided for any 2 elements I take, with x1 being less than x2, its images are such that f at x1 is less than f at x2, and likewise for decreasing functions. Now the question becomes is how does this relate to our slopes of our tangent equations? Well, how this relates to our slopes of our tangent equations is that take a look at the following graph here. What I've done is I've done a rough sketch of our tangent equations at various points on this graph here. And notice we can see visually that our function is increasing on this interval here. We have an increasing function. And notice all of its tangent equations, the slopes are positive. Likewise, we see here that our function is decreasing on this interval here. And we can see also that all of our tangent equations, the slopes are all negative. So from this, we can deduce an idea that f prime at x is greater than 0. Let's say on an interval I, then f is increasing on I. So if f prime of x is greater than 0, i.e. my slopes are positive on a particular interval, then that function is increasing on that interval. Likewise, if f prime at x is less than 0 or negative on a particular interval, then that function is decreasing on that interval. So now you can see here we have now a test using our derivatives and our slopes to determine whether a function is increasing or decreasing. If its derivative is positive on a particular interval, that function is increasing. And if a derivative is negative on a particular interval, that function is decreasing. Let's look at some applications of this. All right, let's take a look at example 1. Notice they gave us our derivative already, my function y prime, right? So the derivative of our function y is already given to us, and they want to know, find the intervals where the function is increasing. Well, what we want to do here is after you've taken your derivative, which we already have that for us here, we're going to go ahead and draw yourself a number line and identify the values of x that make that derivative 0. Well, if I let x be negative 3 and I let x be negative 1, those are 2 values where my derivative is 0. Now what we want to do here is pick a number in this interval. Any number at all. So let's say I pick a number greater than -1. Let's say we pick 0. If I evaluate my function, in this case f prime, at 0, you're going to end up finding that it's greater than 0. So that means on this interval, the interval greater than -1, f prime is greater than 0. Now pick a number on this interval here. Let's say we take f prime between -1 and -3. Let's say f prime at -2. If I evaluate my derivative at -2, we end up getting the derivative is less than 0. And now if my derivative is less than 0, that means on this interval, everywhere on this interval, the derivative must then be negative. And because of that, the function would now be decreasing. And lastly, pick a number less than minus 3. So let's say f prime at negative 5. Summing that into this expression here, we'll find that the derivative is positive. And because of that, f prime is going to be positive on this entire interval. Well, like as we just discussed, if my derivative is positive on this interval, then it must be the case that f is increasing on this interval. In this case here, f must be decreasing on this interval. And lastly, on this interval here, f must also be increasing. So to finish this off here, we say that the function is going to be increasing. Well, it's going to be increasing from negative infinity to negative 3, union negative 1 to infinity. So as I read this number line from left to right, we can see we're increasing here. That's going to go from negative infinity to minus 3, and then from minus 1 to positive infinity. Notice here I don't include the endpoints, and this is very important. We have open circles on these values, because what happens is at minus 3 and at minus 1, your derivative is actually equal to 0. And because of that, that's when we have a change in direction. So notice here, this change in direction happens at minus 3. The function goes from increasing to decreasing. And likewise, at minus 1, we have another change in direction. The function goes from decreasing to increasing. So whenever you're talking about intervals or increase or decrease, we never include the values that include the derivative at 0. So there's always going to be open circles on these values here. Now notice, I know that because I picked a value in this interval, and I got that value when the interval was positive, I then concluded the entire interval must be positive. Because if it wasn't, we would have found another value for our derivative, and we would have partitioned that interval again. If for some reason this derivative went from positive to negative, it would have had to have crossed the x-axis, f prime would have had to. And in which case we would have found that in our factored derivative. Also notice that f would be decreasing on the interval negative 3 to negative 1. All right, let's try another. So for this question here, they want us to find the intervals of increase and decrease for the function, and they give us this function here. So let's take a peek at this one here. So we're going to go ahead and calculate our derivative. So g prime at x is going to be 4x cubed minus 12x squared minus 16x. At this point here, we have to find when the derivative is 0, so I have to factor this. So factoring out a 4x here, we end up getting x squared minus 3x minus 4. And I can factor this a little further here. We have a quadratic that'll factor to x minus 4x plus 1. So therefore, a factored form of g prime at x is going to be this expression. So now what you want to do is draw yourself a number line and identify all the points where your g prime at x is 0. Well, that's going to be, we got x is 0, x is 4, and x is minus 1. Now you pick a value within each interval. So in this case here, pick a value greater than 4. If you pick a value greater than 4 and sub it into our g prime at x, we're going to find that it's positive. If I pick a value between 0 and 4 and sub it into g prime at x, you're going to find that that value will be negative. If I pick a number between negative 1 and 0 and sub that into here, so let's say we put in minus 0.5, you sub that in here, you're going to end up getting your derivative is positive. And lastly, for our last equation, you sub a value into here, you're going to get negative. Now you might be tempted to think that it always alternates like this, and that's not always the case. Depending on the structure of the original function, if it has any vertical asymptotes, points of discontinuity, whatever that may be, that doesn't always happen. So be mindful of that and still sub the points in and make sure. So at this point here, we want to continue. So I want to find out when my function is increasing or decreasing. Well, I have my functions increasing on this interval and this interval as the slopes are positive. Positive slopes mean my function is increasing, and negative slopes mean my function is decreasing. So therefore, we have here g is increasing on the interval negative 1 to 0, union 4 to infinity, and g is decreasing on the interval negative infinity to negative 1, union 0 to 4. Let's go ahead and look at another example. All right, let's take a look at the next example here. So for example 3, find the intervals of increase or decrease of the following function. So we first have to take our derivative. So in this case here, f prime at x is going to be the first times the derivative of the second. Don't forget, using the chain rule, you have to take the derivative of the inside. Plus our second function times the derivative of the first is just your 1. So now in this situation here, we're going to have to simplify this a bit. So if I take a look here, I'm simplifying this. I'm going to write it back into root form. Again, I find it much easier to see what simplification we can do by go ahead and putting this in root form. I can kind of see where everything's at. And now what I'm going to do is I'm going to multiply top and bottom here to get a common denominator of the root of 4 minus x with a 2 in front as well. So by doing that, we end up getting f prime at x will be negative x plus 2 times 4 minus x all over 2 times the root of 4 minus x. Cleaning up the numerator, we end up getting here negative x plus 8 minus 2x over 2 to the root of 4 minus x, and simplifying, we have our answer here. So now I know that f prime at x looks like this. So same idea as we've been doing before. We want to go ahead and draw ourselves a number line, and we want to identify 2 points. Points where the derivative is 0 and points where the derivative is undefined. Well, the derivative is going to be 0 when x is 8 over 3. We also have the derivative undefined at 4, so I'm going to put an open circle on that. So now let's go ahead and pick values in these intervals and see whether their derivative is positive or negative. However, if I pick a value in this interval here, I would have to pick a value greater than 4. But recall, f at x was x times the square root of 4 minus x. Well, that means that in terms of the domain of f at x, 4 minus x must be greater than or equal to 0. Solving for x here, we end up finding out that x must be less than or equal to 4. So therefore, if I pick any value in this interval greater than 4, my function itself is undefined on that interval, so the derivative does not exist, as the function does not exist greater than 4. Now going back to this f prime here, if I pick a value between 8/3 and 4, let's say we pick 3, subbing a 3 into here, you'll notice the top will be negative, the bottom will be positive. Negative over positive is negative. And lastly, if I pick a value in this interval, let's say 0, sub a 0 into here, we get positive, and likewise we get positive, which gives us positive. So to summarize this, my function f is going to be increasing on the interval negative infinity to 8/3, and your function f will be decreasing on the interval 8/3 to 4. Again, notice here we have open brackets on these endpoints. The reason for that is, again, is at 8/3 my derivative is 0, and that reflects a change in motion. And at 4, our derivative is actually undefined. All right, let's look at another problem. For the following example here, we want to find intervals of increase or decrease for the following function. So once again, we have to take our derivative. So in this case here, dy dx is going to be drop down that 2/3, subtract 1, and then take the derivative of the inside, which will be 2x. So let's simplify this a bit. So in this case here, dy dx is going to equal 4x over 3 times the third root of x squared minus 9. Now again, we want to find values of x such that the derivative is 0 or undefined. So draw yourself a number line. And we'll notice here at 0, we have the derivative is equal to 0 when x is 0. Also at plus or minus 3 here, we have points where the derivative is not differentiable. My f prime is not differentiable. So now we kind of want to examine these intervals. So if I pick a number greater than 3, let's say 10, and we were to sub that in, we'll get a positive value. Now pick a number between 0 and 3. Let's say I pick a 2. Subbing in a 2 here, I'm going to get a negative value. Pick a number between negative 3 and 0. Let's say negative 2. Subbing this in here, we're going to get a positive value. And lastly, pick a number less than minus 3, let's say negative 10, which is going to result in a negative value. Okay, so in this situation here, if you take a look, we have our function, in this case, f, is going to be increasing on what intervals? Well, it's going to be increasing here and here. So therefore, from negative 3 to 0, union 3 to to infinity. And likewise, your function will be decreasing from negative infinity to negative 3, union 0 to 3. All right, that concludes today's lesson on increasing and decreasing functions. Thank you.